Let's look at Newton's universal law of gravity. Newton said every particle in a universe attracts every other particle with a force that is directly proportional to a product of their masses and inversely proportional to what? To a square distance between their centers. Let me say you are given object A and object B. Should I say particle A and particle B? Newton said object A, of which is an apple, is attracting object B, that is Earth, with a force or a force of attraction that is directly proportional to the product of their masses and inversely proportional to the square distance between their centers. But because we're talking about an apple is of very small radius. So when we're calculating an attraction force between apple and Earth, you have to ignore the center, or should I say the radius of an apple or a human or anything that is an object on Earth that is calculated against Earth. It's very small to be negligible, so it's going to make very little change. But for object like this one, object 1 and object 2, or the other one, object 2, if you have to calculate the force between them, you have uh, to put their masses there, masses respectively, mass 1 and mass 2. But when it comes to radius, you're going to put the distance between them, but also mention what is there. You have to mention their radiuses. So what you put in exactly on that radius square, you put in radius of the first body plus distance between two bodies and the radius of the other body, and you square them. But most cases in your question, you are to be told that the distance that you told is from their centers, so you don't have to worry about this. But for some cases they get tricky. They just give you a distance between bodies and they give a radius of each body. Or maybe for Earth, you have to find the radius of Earth in your data sheet. And also it same goes with the mass of Earth. Radius of Earth is in your data sheet and mass of Earth is in your data sheet because they are mostly used in your calculations. Back to my case of an apple and Earth. One of my friends used to ask me, or once asked me some question that just sometimes triggered me and sometimes I thought and just got the answer. He said because of Newton said every object are attracting each other with same forces that is directly proportional to their mass, inversely proportional to the square distance between their centers. He said because the apple is pulling Earth as much as Earth is pulling as much as Earth is pulling the apple. So is the apple moving toward Earth or is Earth moving toward an apple? So whenever we see things dropping, it's like, are things really dropping down or we moving toward them, as much as Newton said? The question is answered by one of Newton's laws again. One of my famous one is said F net is equals to ma, where a is acceleration, m is mass. Okay, this law said that force that you put in is directly proportional to acceleration. Okay, because here they of very same force, we ignore this. And the next thing that this law said it's also say that acceleration is inversely proportional to mass. So that where the answer that's why you get your answer for that question. Who is moving? Is an apple or is Earth moving toward an apple? Let me elaborate on this. Because mass is of big Earth is of big mass compared to an apple. It will have less acceleration. Simply it will not move because the apple is of extremely low mass. It's going to accelerate very fast. It will be noticeable. So for an Earth and apple, they are really pulling each other. But then, if the two guys are fighting or pulling each other, the one with less mass is going to move, and the one with less mass is going to move. Simple. Yes, they are pulling each other because of newtons. We say acceleration is inversely proportional to mass. Yes, then apple is moving, the earth is not moving. The other thing that I've been not mentioning all this long, but it's there on our equation, is g. The g that you see there, you're going to find it in your data set. It's a constant of 6,67 times 10 power 11. Power 11. It's a constant, and you're going to find it there on your data set. And I have it just here. It is a universal gravitational constant. So yeah.